We're going to do a whole lecture on spin-orbit interaction and how it manifests in quantum devices. What effects can you see in semiconductors? You all know spin-orbit interaction from atomic physics. It splits energy levels in atoms. It has a relativistic nature. You may remember this formula from your basic physics. Formula contains spin, momentum, orbital, degree of freedom for an electron orbiting the nucleus, an electric field from the nucleus. And then to do the Lorentz transformation, and this electric field transforms into a magnetic field, and then it acts on spin. In semiconductors, the formula is actually very similar. So you can define an effective spin-orbit field, which is a magnetic field, but it's not real, it's effective. So you don't have to apply it externally, or it will not influence an external magnet. Only a spin inside the crystal lattice will feel this field. So it's an effective field. It boils down to some constant, which is a material property. In this case, it's alpha, because I'm writing a formula for a Rashba effect. And then a vector product of spin and quasi-momentum, momentum inside the lattice. So you can see that here you also have actually a vector product of spin and momentum, because momentum is this will give you a vector perpendicular to both of these, and then you multiply it by spin. So in this in this specific formula, this is a so-called Rashba effect, and here alpha also contains some kind of an electric field. It's an electric field felt by the electron due to for example, being close to the surface or felt from the gate. So a real electric field that you can create and apply. So in the case of Rashba effect, we will talk about it in the next slide. Here we just play with a notion of this effective field. It's a field, as you can see, if you want to know this field, you have to do these terms and then divide it by the G factor of an electron and the Bohr magneton. So you just take the spin orbit energy and convert it into field like that. You get a good number. So then what that field is, it is dependent on, oh sorry, I forgot spin here. I have to have spin. So this spin is still here. Yeah? But the rest is field. So the field is dependent on material property, and also dependent on momentum. And so then it means that if the electron turns backwards, the field will actually change. The field will point in the other direction if the electron turns backwards. If the electron slows down, the field becomes smaller. So it's a field that is produced entirely by the motion. If the electron stops, there is no field. Yeah. If you just apply this formula to electrons in one dimension, you get what I've drawn over there with those pictures. So in one-dimensional systems, remember we have subbands, we have these parabolas, momentum, energy versus momentum, and they are spin degenerate at zero magnetic field. But if you just say that you want to add an extra energy to these electrons, which is dependent on spin, and it's a linear term, then what you do is you take these two degenerate parabolas, add a linear term, you can rewrite it as a parabola which is displaced. Actually, it also comes down a bit. So this axis is drawn just schematically. Compared to that parabola, this one will come down a bit. From if you add a linear term like that to a k-squared term, which is just kinetic energy in the parabola. And so that kind of lifts the spin degeneracy, because for now, for a given k, except for k equals 0, where spin orbit field is 0, so there is no effect. But for any other k, spin down and spin up will have a different energy. And that's a consequence of spin-orbit interaction. And the stronger the spin-orbit interaction, the larger is this spacing between the parabolas. So if you want to know the strength of spin-orbit interaction, you can go and measure this cross point and calculate how far it is from 0. This will be the spin-orbit energy. And this will be some kind of a spin-orbit characteristic momentum, how far the bottom of this parabola is. So spin-orbit interaction lifts spin degeneracy, but in a different way than Zeeman effect, right? The Zeeman effect, the parabolas move like that. And in the case of spin-orbit effect, they move like that, in the other direction. So that actually also tells you that this interaction preserves time reversal symmetry. Because time reversal symmetry means if you reverse all the velocities in your system, then the system will go back to its state after a time t. So if you let all the spins fly for time t, reverse all the velocities, they'll go back. So, or in other words, if you reverse time and magnetic field, then the system will be identical. So this kind of interaction, this term and this band structure, does not violate time reversal symmetry. Whereas magnetic field does, because you're introducing an energy difference between spins for all momenta. So then if you reverse the field, the system will not come back. Okay. For this particular form of spin-orbit interaction, where energy is linearly dependent on momentum, it is very useful to define a spin-orbit length. So it's a length over which spin undergoes a full rotation due to spin-orbit field. So if a spin starts like that, spin-orbit field is pointing like that, and it's flying like that in a straight line, it will rotate constantly. And after traveling a certain length, it will rotate by 2 pi and come back to the same orientation. That would be the spin-orbit length. Sometimes it's defined as a spin flip length. That's half the full rotation, just the pi rotation of spin. So why is it useful to think about spin-orbit length? Well, for such linear terms, if you go faster, also spin-orbit field grows larger. So over the same length, you do the same rotation. So no matter how fast you go, the length remains the same. So then spin-orbit length is not dependent on momentum. It is just determined by this alpha. So you can write a spin-orbit length in terms of this alpha. It will be something like h bar over m alpha, something like that. And so if you know spin-orbit length, if you measured it or looked it up, then you know the spin-orbit strength in a given material. And here are some examples of the materials that we already encountered in this class. Gallium arsenide is the one that we talked about the most, perhaps. So in this gallium arsenide, aluminum gallium arsenide 2-degs, the spin-orbit length is pretty large. It's 10 microns. That means spin-orbit interaction is comparatively weak. Still, you can see many, many effects of it. So the longer it takes for spin to flip under the influence of this field, the weaker is spin-orbit interaction. So in indium arsenide and these nanowires that I work with in my own group, indium arsenide, indium antimonide, Actually, it is much stronger, about 2 orders of magnitude stronger. So you are in a 100 nanometer range. And you can also appreciate the meaning of this length, because remember, various length scales determine how large a device has to be in order to see these effects. So in a gallium arsenide 2DEG, device has to be microns large or even more to see some of the spin orbit effects. Though some others can be seen even in tiny dots, but they are very weak. And in indium arsenide, already in a 100 nanometer device, spin undergoes a complete rotation, just going from one side of the device to the other. And now if you want an even stronger spin-orbit interaction, perhaps you would be interested in what they study in Jeremy Levy's group, lanthanum aluminum oxide, strontium titanium oxide interfaces. There people have reported spin-orbit length in nanometers. So very, very strong spin-orbit interaction. Now in something like oxide 2DEG, there could be different reasons why spin-orbit interaction exists. We are going to discuss here just spin-orbit interaction in semiconductors like gallium arsenide. Just for consistency, spin-orbit interaction in these materials comes from the band structure. So remember the bands, the valence band, conduction band. So the way you calculate these bands, remember you put in a crystal lattice and you use some kind of an approximation to solve a Schrodinger equation. You cannot solve the full Schrodinger equation for a crystal, of course, but you can use an approximation. In that approximation, you get bands of allowed electron states. Well, if you do go through all this math, some of the bands actually happen to be coupled, and these couplings produce terms which are products of momentum and spin, terms like that. So from the band structure, you get a spin-orbit interaction. That's the first thing I wanted to say. And in the case of gallium arsenide 2DEGs, yeah, very convenient system to study, there are two distinct effects that give spin-orbit terms in the Hamiltonian. Now, one of them is the Rashba effect that I already mentioned to you. So the one that closely resembles atomic spin-orbit interaction, because there is an electric field involved that you can write down in the formula here in this alpha. Well, Rashba spin-orbit interaction is produced when you have asymmetry in confinement of your electrons. So asymmetry like this. Remember, this is the diagram of the band edge of the conduction band for electrons in the gallium arsenide, aluminum gallium arsenide. So this was aluminum gallium arsenide. This was gallium arsenide. And electrons are trapped at this interface in this quantum well, triangular quantum well, between gallium arsenide and aluminum gallium arsenide. And they're created, induced by these positive dopants in this well. So one thing you can see is this well is highly asymmetric. On one side, you have a very sharp edge, and on the other side, you have a smoother edge. So it's this asymmetry that you can kind of write down as an electric field. So the asymmetry in the band profile in space, in real space. So this is the growth direction of the heterostructure. You grow these different layers, and you create asymmetry in this structure. So Rashba effect comes from structural asymmetry, structural inversion asymmetry. So if just for the sake of argument, if we had a very symmetric well here, for example, a square well, right, like particle in a box problems that we're used to from quantum mechanics, a completely symmetric square well, so Rashba effect would go to 0. And if we had a well which was tilted the other way, so a sharp edge here and a smooth edge this way, this constant alpha would flip its sign. Now, people have actually played with it because they can grow all kinds of different structures, and they have grown a wells where they could tune the asymmetry from left to right and have them be asymmetric this way or asymmetric that way, and they observed the sign of this coefficient flip. And so this is an electric field created by this asymmetry. Whenever you have a, remember, whenever you have a slope in your potential, that is like having a force or a field, an electric field. So this is a kind of field. And if this is a 0, 1, 1 growth direction in semiconductor terms, then in this plane, spin-orbit interaction will have this form. So py times sigma s, px times sigma y, and there are signs, appropriate signs here. And this turns out to be just a vector product of sigma times p. Okay, in this case I used k. So if you think about which way these fields are pointing, so for energy I take the absolute value, but actually it matters. The direction of the field is given by this vector product. So which way the fields are pointing, so effective spin-orbit field is kind of perpendicular to momentum for any value of momentum. So if this is a Fermi surface in some axis, then whatever momentum you have, this Rashba effect gives you a field perpendicular to your momentum. So very easy to remember. If you go this way, Rashba effect will be this way. Or if alpha is the other sign, it will be this way. If you flip and go backwards, Rashba effect flips, right? If you go this way, it's pointing down. If you go back, points up. So very simple dependence. Now, there is another component of spin-orbit interaction present in gallium arsenide. And I must tell you, the two constants, alpha and here it's beta, they are very close. So the two terms are of equal importance. And once again, written down in for a gallium arsenide 2-deg. So in the plane perpendicular to 0, 0, 1 growth direction, you have this kind of dependence of this other term. X times x, y times y. So a little bit different. The math is a little bit different. The consequence of it is that fields are pointing like that. So sometimes they're pointing out, so along the momentum, sometimes in, and sometimes perpendicular. So a little bit, so just here you have x, x, and it gives you this. And if you have y, y, x, y, y, x, it gives you this simpler form. So this is just math. Now, what is this coming from? This is called the Dresselhaus term. And it comes from inversion asymmetry that is present in the crystal lattice itself. So due to the simple fact that there is no inversion center in a cell. So this effect is not tied to any interface, though the strength of this beta is affected by confinement. But this effect would be, in principle, present also in a bulk crystal of just gallium arsenide without any interfaces. You take a piece like that, and the electron right in the center, away from any interfaces, it will experience some strength of Dresselhaus spin-orbit interaction. So it comes from internal electric fields inside the unit cell. I think that's all I want to say in this lecture about the origins of Dresselhaus spin-orbit interaction. We can discuss it in more detail, have to involve some band calculations or more arguments. If the crystal symmetry is different, so this is called a zinc blende crystal. symmetry. I think it's the same as for diamond maybe, but in diamond both atoms are the same, and here they're gallium and arsenide. But if you were to go for a Wurtzite crystal structure, for example, then Dresselhaus term will not be there, but there is its own Wurtzite symmetry, because in Wurtzite it makes a difference whether you go this way or this way. It's a different crystal symmetry, and it gives rise to a different spin-orbit interaction. So the point is, we're not going to go into deeper into band origins of these effects, but whatever we deal with, whatever spin orbit we deal with, we want to know how it depends on momentum, what is the strength of it, and then we can just build a device around it without worrying too much about the origin of it. Okay, so now let's look over here. Here it says X and Y, right? X and Y, X and Y. Actually, these axes are not X and Y. They're 45-degree rotated. So X and Y axes would be these two axes. So this would be Y, this would be X. The reason I plotted it like that is because in this basis, which is 1, 1, 0, 1 minus 1, 0, things become, some of the things become more apparent. For example, along this axis, Rashba and Dresselhaus are pointing both perpendicular. And actually, they're pointing in the opposite directions. This one pointing up, this one pointing down. Also along this axis, same thing. Both point perpendicular, now in the same direction. So this one pointing this way, this one also pointing this way. And if you go to negative direction on this axis, they're pointing backwards. And remember, we have both. We have both in gallium arsenide in these two decks. And so we have to add them up. Well, turns out if they are exactly the same strength, if alpha is exactly equal to beta, and Rashba is exactly equal to Dresselhaus, we get this very interesting degeneracy happening. No matter which way you fly, you can go this way, or that way, or that way, spin orbit field is always pointing along the same axis. Along 1, 1, 0 axis in this case. So this is very different than Rashba effect, right? Remember I told you Rashba effect is the simplest effect. You fly that way, Rashba effect will be perpendicular. Fly that way, same perpendicular. And the same strength. Here, very different. So this has some consequences. For example, if you want to take advantage of spin orbit effect, if you want it to be strong, don't associate it with motion along, don't hope for a field in this direction. So don't try to move electrons this way and hope for some field. There will be none. So better associate with motion in this direction. Also at this degeneracy point, something interesting happens to the spin orbit length, so to say. Because now, let's imagine we are in 2D, and there are electrons flying in all directions. It's a disordered gas or a large sample, so they're scattering, they're moving in some trajectories, but motion along one of the directions has no consequence for spin rotations. Only motion in one direction matters, not in the other. So that leads to the creation of some beautiful spin patterns. For example, persistent spin helix. This is something that was observed, a group at Berkeley. This is one of the first papers. They had a Nature paper a couple of years after that. So what they've done is they've initialized spins in a certain direction, like up, for example, with a laser. Polarized spins with photons. And then they let them evolve. And the spins, they form this pattern, spin helix. So if they do it with away from this degeneracy point, spins would completely randomize as they fly around. And they don't form any patterns. But at the degeneracy point, you can preserve a certain spin order, even though electrons are moving randomly and they're supposed to be randomizing spins. There is a certain spin coherence effect that stays behind. This also introduces the historical role of spin-orbit interaction to you, which is a spin randomization, spin relaxation in semiconductors. The people were trying to study spin properties in semiconductors for 30 years, maybe even longer, and they were finding that spins are short-lived in semiconductors. That's before any nanoscale or quantum transport, just even the bulk studies on semiconductors. And spin-orbit interaction was to blame because electrons were free to move, and therefore spin-orbit fields were producing random rotations of spins. So you move this way, and spin-orbit field is this way, and then you scatter back, and it starts spin starts precessing along a different axis. So spin relaxation, spin randomization was the role of spin-orbit interaction. And then if you have this, for example, then you can build a device where you insert spins at this distance, and you withdraw them here, and this is exactly the spin rotation length. They have recovered to exactly the same position, even though they were flying randomly here. That's because of this cancellation. So people have proposed to build a spin transistor based on this cancellation. This paper, for example, Schliemann is one of such proposals. Okay. Now, why did I decide to spend a whole lecture on this one effect? Well, one reason is because I know about it a lot, because I've studied it for several years, which is not a bad reason. Maybe I can give a better lecture on this than on something else. But also, I think it is worth your time, because this effect, from being this ugly duckling, a cause of spin relaxation and annoyance to everybody for decades in semiconductor business, it became a very influential effect over the last, especially over the last few years. Many new discoveries rely on this effect, topological insulators, for example. So here in this slide, I list the history of spin-orbit interaction. And you can see that actually right about after the first line, there is a transition from thinking about it as this bad effect to trying to come up with ways to use it, and particularly use it in devices, in quantum transport and so on. This paper, Data Das, is an extremely famous paper. This is a paper that maybe launched the field of spintronics. It's a theory paper, and this effect maybe has been demonstrated only a couple of years ago, and the quality of that demonstration, well, it's rather convincing, but to use that as a spin transistor, we have to go still a long way before that happens. But what these people proposed is, actually the paper is called an electrical analog of an optical modulator with spins. They proposed this device. Let's have a 2-DEG with spin-orbit interaction, and let's slap a couple of ferromagnets on it, some kind of spin-injecting contacts. So they inject electrons with this spin polarization. So electrons start with spins going like that, and then going from left to right, they rotate by some angle. So if they arrive with the opposite spin, if we fit a spin orbit length here, or half a length, then they will have a hard time going into this ferromagnet, because this ferromagnet only accepts spins going this way. So then, instead of going like that, let them go the full rotation and come back like that. Then they will have an easy time getting in. So this is a device where spin of arriving electrons influences the conductance through this device, or resistance. And this is gate controlled. What they proposed is that they wanted to change the rotation angle of these spins with this gate. Now remember, you cannot do that by just changing the density of electrons. Remember, what this gate does in all of our examples so far was that this gate would change the density of electrons and change the velocity of these electrons, the Fermi velocity. Now remember, spin orbit length is independent of velocity. There's a cancellation. So what you have to do is you have to change the asymmetry in the quantum well. You have to change the electric field that electrons feel. And you have to change it by a lot to go from full rotation to half rotation in some distance. So it turns out that's hard. In gallium arsenide, this asymmetry, this triangular well, is so strong that to affect that is very difficult. I don't know of a single study where that worked very well. But this idea inspired many other proposals, like the one I listed in the last slide with the cancellation of Rashba and Dresselhaus effects. That was another idea. Now, I want to highlight this effect. I'm hoping to discuss it separately in a lecture on Hall effects. But this is an analog of Hall effect, but with spins. You send a current through a semiconductor. So you have an electric field applied. And under the influence of that electric field, moving electrons, so the electric field creates a motion. And there is spin-orbit interaction where now we are looking at the opposite effect of spin-orbit interaction. So before I discussed that motion of electron influences the spin. This is the opposite effect. So spin of an electron influences the motion. Well, it is quite reasonable because the term is spin times motion. So you can control spin by moving electrons back and forth, or you can control motion of electrons by playing with their spin. So this is a wonderful demonstration of that, because they just send a current of electrons, and depending on their spin, electrons prefer to go left or right. So they have detected a spin accumulation of, say, spin down on one side of the sample and spin up on the other side of the sample. Just like in a Hall effect, you detect a negative charge on one side of the sample and positive charge on the other side of the sample. Here, the same with spin. So spin of an electron influences the motion of an electron. And you can imagine some usefulness to this effect as well. If you want to start with an unpolarized current and create spin accumulation of a given spin, we'll send it through the semiconductor, and all the spin downs will go to one side, and you can collect them here. If you want to use them as to create a spin current, for example, in a spintronic circuit. So this was great. I'm hoping to talk about this today, but basically this idea that when you move an electron, it experiences an external field, you can use it for control of spin of a single electron. You can even build quantum bits based on that. And finally, this is sort of the new era, the latest developments that involve topological states and topological phases in condensed matter physics and in quantum transport. So now we have quantum spin Hall effect. We have topological insulators. We have Majorana fermions. In all of those, an important ingredient is spin-orbit interaction. So quantum spin Hall effect is a quantum limit of this effect, much like the quantum Hall effect is the quantum limit of normal Hall effect. So in this case, you have edge states which have a chiral spin character. Okay. So I hope this slide convinced you that this interaction is profound. It is also fun. You can play with spins. You can play with electrons. And that it's worth spending an hour discussing this interaction. We're going to go through things that are familiar to you already from before, because we thought about one-dimensional systems, zero-dimensional systems, two-dimensional systems. So now let's talk about the zero dimension. Let's apply the concept of spin-orbit length to a quantum dot. Quantum dot is something small where we can find electrons. Well, we can play with its size, actually. But what matters is how large is the quantum dot compared to spin-orbit length. So if we're talking about a quantum dot in gallium arsenide, which has a few electrons, 1, 2, 3, and so on, that is maybe 50 nanometer size, 20 nanometer size, something very small. Spin-orbit length in gallium arsenide would be 10 microns. So the dot will be like that compared to spin-orbit length. And so if you imagine an electron as a quasi-classical dot, a spot moving inside the quantum dot, flying inside the dot, then spin-orbit effect has very little influence on spin. As the electron flies in that little dot, spin is always pointing this way. In some of the other semiconductors, in smaller band gap, like indium arsenide, indium antimonide, by the way, spin-orbit effect tends to grow as the band gap tends to shrink. So in those, you get in this regime where this length is maybe 100 nanometers, and the dot is maybe 20, 30, 50 nanometers. So think about it. The size of the dot is comparable to spin-orbit length. Means that inside the dot, can you even define spin very well? The answer is no, you cannot, because just inside the wave function of an electron, at different points, the electron would kind of have different local spin, because it kind of flies back and forth through the dot to make the wave function. And as it goes, it experiences a pretty substantial spin rotation. So the statement is that in quantum dots with strong spin-orbit interaction, spin is a bad quantum number. It's not defined. So we have still eigenstates in these dots, but they are spin-orbital eigenstates. The way to get those eigenstates is, well, if spin-orbit is not way too strong, you can just do a perturbation theory. You start with your pure spin states, and then take a matrix elements of spin-orbit interaction according to the perturbation theory formulas. And then, in principle, spin-orbit interaction would mix all the orbitals in the dot with both spin states. So everything is mixed to a different strength. If you want to just get a kind of emulate the effect of spin-orbit, you can just think about coupling the lowest orbital to the next orbital. That's probably the strongest effect anyways. So instead of this sum, you will just have one extra term, and this will be the 0th orbital, and this would be the 0th orbital, this would be the first orbital. So spin-orbit interaction would create a correction to quantum levels in a dot, and it will mix spin up and spin down. So you will have spin up and spin down in each eigenstate, and it will modify the energies of these eigenstates. But because this interaction does not break time reversal symmetry, there will always be a doublet of these eigenstates. Just like you have a spin up and spin down doublet, the spin orbit eigenstates will also be a doublet. And that doublet is called the Kramer's doublet. So it's not spin, but Kramer's degree of freedom. Now you can imagine that the spin-orbit interaction then influences various properties in quantum dots. And I already told you that the size matters as well. So one of the things that it influences is the G factor of electrons. In fact, in semiconductors, we always have a kind of an effective G factor with a star, G star. And it comes from spin-orbit interaction. So remember, G factor, just for a free electron, that's just a constant which tells you by how much the energy of an electron changes when you apply a magnetic field. G mu B formula. Well, in semiconductors, again, you have a G mu B formula, but this G can be anything. Doesn't have to be 2 like for a free electron. And the reason why that's the case is because of spin-orbit interaction, because spin and orbital motion are coupled, and as you apply magnetic field, you change the orbital motion. So you add energy to the electron, and that energy exhibits a Zeeman splitting. So effectively, it looks like spin has a larger G factor. So effective G factors can be very different. In gallium arsenide, it's minus 0.44 compared to free electron value of 2. In indium arsenide, it is about minus 15. And indium antimonide, it's about minus 50 in the bulk. So when you don't confine electrons, and spin-orbit effect is the strongest. Now imagine I start confining the electron. And I confine it so strongly that it doesn't fly anymore, doesn't move. It's a small wave function, and then it is a very small wave function compared to spin-orbit length, bulk parameters. Extreme confinement, maybe 1 electron volt. Well, actually, in that case, you gain again the G factor of 2 plus 2, because electron is no longer moving whatsoever. The orbital degree of freedom is quenched, and so you cannot put any energy into that orbital degree of freedom. This is confirmed by experiments, by calculations. Here I show a couple of graphs that illustrate this effect for, they have calculated it for a system which is a nanowire with a quantum dot which is a disk inside the nanowire. So it's a disk like that, and they can play with L, the size of the disk. So when they have a very fat disk, they calculate very large G factors. So here, remember I was saying minus 15. This is indium arsenide, so they are at around minus 11. So it's already confined compared to the bulk, but it is very large. And as they shrink the disk, the G factors, they decrease. They become smaller until, and they tend towards plus 2. And this is an experiment, not so many data points, but a few. You have to make a new device for each. It's time consuming, but these people have measured something like that. They don't know the sign of the G factor, so they plot the absolute value. They just measure it from spin splitting of the excited states in quantum dots. And they see that for very large dots, they have a large G factor, and as they shrink the dot, the G factor shrinks. So we are quenching orbit by confining electrons more, and we are suppressing the effect of spin-orbit interaction on G factor. Now, you can also imagine that if your quantum dot is anisotropic, you'll get different G factors in different directions. So for example, this disk is anisotropic. So if they rotate magnetic field, they would get something different. You can think of it as what matters is the size of the dot perpendicular to the field, because you're coupling the orbital motion to spin. So when you are pointing your field this way, it's this orbit that matters. So here we have, actually this is our data. We have done a bunch of measurements of G factors in nanowires in quantum dots defined by gates. We don't know their shape very well. They're not perfect disks. They're not grown in a nanowire. They're just defined by gates. But we can kind of read out their shape from the anisotropy of G factor. So for example, here is a curve, shows G factor as a function of angle of a magnetic field. You can see that the G factor is large at the angle of 0, so along the wire. That tells me that direction perpendicular to that, this direction is maybe larger. So the dot is a little bit like that, a little bit like that disk actually. So when we go perpendicular, so 90 degrees coupled to that direction, that is actually smaller. So we are more confined, perhaps. Another interesting thing is that the difference between the two curves is that we made the dot larger, the overall dot. Here it was defined with 3 gates, and here with all 5 gates. So we really made it bigger. And the anisotropy remained roughly the same, but the entire curve shifted down. So all the G factor values for all directions grew. So less confinement, larger G factors. So again, it kind of confirms. So this is an effect of spin-orbit interaction that is embedded in the band structure of semiconductors. And you can see that in the measurements in quantum dots. But here we were sort of extracting this effect from deducing it from the value of G factor. We have to then apply the full force of the band structure calculations to get to the spin-orbit interaction. That's not so handy. There is actually a way to measure spin-orbit directly. And quantum dots offer, again, us this opportunity. It comes from the fact that we can create different spin states, like spin up and spin down, or in this case I use singlet and triplet. And by magnetic field, we can make singlet and triplet degenerate. So singlet stays in one place, and triplet is at a higher energy. It's in the next orbital. Yeah? And then we apply magnetic field, and the triplet splits in 3, T0, T plus, T minus. And of those, T minus, or T plus, comes down and down and down until it meets the singlet. So the other way around. Singlet doesn't move, and triplet moves. Now, when they are degenerate, spin-orbit interaction couples singlet to triplet. Because orbitals are coupled via spin-orbit interaction, and therefore different spin states can hybridize. So when you bring them to degeneracy, they will exhibit level repulsion. And the size of this level repulsion directly tells you the spin-orbit interaction coupling strength. So literally what I just explained can be measured in quantum dots. This is an example where we have 2 electrons in the quantum dot. And so we are looking at levels which are singlet and triplet levels of 2 electrons in a quantum dot. But we are using a second dot as a probe. We are using a spin blockade effect, like I described in the last lecture, to do this spectroscopy. Because in spin blockade, we have a means to see spin transport directly. So this is maybe just a technical point, but this explains these indices, 0, 2, 1, 1. So like the previous story of spin blockade. The scan along this axis is the detuning scan through the triangle, like this. And when you are doing this cross-section, you are probing with your 1, 1 levels the 0, 2 levels. So it's like in the last lecture. But all you need to know today is that this is the energy axis. this is the, at zero magnetic field, this is the orbital splitting between singlet and triplet. And this slope is the Zeeman slope, and this level repulsion is the anti-crossing of the two levels. So far away from the anti-crossing, this is a singlet state, and this is a well-defined triplet state. And at the anti-crossing, singlet and triplet are mixed. So these two resonances are then superpositions of singlet and triplet. And going through the anti-crossing, this is a singlet and this is a triplet. But notice the two lines just continue continuously. So if you go along the line, you are triplet, triplet, superposition, singlet and triplet, and then singlet. If you go along this line, you are singlet, 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 superposition, triplet. So this is a common thing in qubits. We also study these anti-crossings. So if you are a bit shaky on that effect, you go back to your quantum mechanics and take a look at these level repulsion anti-crossing effects. This is just two coupled quantum levels. But in this particular case, spin-orbit interaction is responsible for coupling singlets and triplets. So if a spin-orbit interaction were zero, they would have no way to talk to each other. One line would just go straight through the other one without this coupling. So then they cross, the two levels cross. And there are no coupled, there are no superpositions, etc. Now another interesting thing we found was that we did this measurement for different orientations of the external field. We rotated the external field again like that, like for measurements of G factor in this plane. And we found again an anisotropy, but that anisotropy was very dramatic. With G factor, it just modulated a bit. Here, for 0 degrees, we had some gap, a couple hundred microvolts. And for 90 degrees, the gap was 0. We could not tell the gap. So this is close to 90 degrees. This gap is almost closed. And this is 0 degrees. So this is along the nanowire, and this is perpendicular to the nanowire. So this is a situation that I just described. The singlet and triplet apparently are not coupled, or coupled very, very weakly, because they almost go through each other, and there is a very small anti-crossing. So we turned off the spin-orbit effect by rotating the magnetic field. And the physical picture for that is very, very simple. It has to do, again, with the concept of spin-orbit field. And it has a direction in space. Now, in these nanowires, we just have Rashba effect. I'll just tell you that from the start. So electrons move along the wire, means spin-orbit field is perpendicular to the wire. Actually, there are many perpendicular directions, but the way we made these devices, it's lying on the gates, it's lying on the substrate, so very likely the symmetry is broken this way. So structural inversion asymmetry field, Rashba field, would be pointing perpendicular to this electric field and perpendicular to the momentum, so it only can point in this direction. That's a 90-degree angle over here. So when we align external field with spin-orbit field, the two fields just add up to each other. So spin-orbit field has no capability of mixing spins because it contributes to the spin quantization direction. Spins are always defined according to some axis, spin up and spin down. In an external magnetic field, spins want to align along this axis. So if a spin-orbit field is perpendicular to that, it will try to rotate spins from that axis and couple singlets and triplets. But if the two fields are collinear, this will not happen. So this is a measurement of the magnitude of spin-orbit effect, also of its direction. And we have used quantum levels that have spin character, opposite spin character, singlet and triplet, in a quantum dot to measure spin-orbit interaction in this material. Just for consistency, I wanted to show you that also spin blockade has the same anisotropy. If you remember from last lecture, I'm not going to spend too much time on it, but remember we had this dramatic lifting of spin blockade at finite field. So this is a field, and this is inside the spin blockade region. At zero field, spin blockade is strong. Blue means zero current. And we increase magnetic field, and we have all this current here. That's because spin-orbit interaction mixes singlets and triplets. And in this diagram, these triplet states, triplet plus and triplet minus, become coupled to singlet, and electrons can go from 1,1 to 0,2 with a high rate. But if we rotate external field with respect to spin-orbit field and line them up, spin-orbit and external field, all the current is gone. Spin blockade is restored. That's because these triplet 1,1s are not coupled to singlet 0,2 anymore. So the difference with the previous slide is only that there we consider 2 electrons in the same dot, and now we consider electrons in 2 dots. And we are asking whether this electron can go across or not. So I just want you to carry out of this the main ideas about spin-orbit interaction, not maybe to follow the details of all these measurements, but the ideas are that spin-orbit interaction couples opposite spin states in quantum dots. Spin-orbit interaction is highly anisotropic, and the relevant parameters to think about spin-orbit interaction are spin-orbit length, that tells you the strength of spin-orbit interaction, and then you compare your device to spin-orbit length, and you can tell a lot about how influential spin-orbit is. But also spin-orbit field direction, because things that get very anisotropic when you take that into account. So singlets and triplets couple and decouple, and so on. This is also an advertisement for an upcoming lecture on spin qubits in quantum dots. These are measurements from Delft group where they have a way to extract spin relaxation in quantum dots. So they prepare a spin in the excited state, spin down, and then they count how long it takes for that spin to relax to spin up. They count, they put statistics, and they plot these rates. This is a spin relaxation rate, which is 1 over spin relaxation time it takes for spin to flip from up to down. So they have a way to extract that, and they believe that the main reason for spin relaxation in quantum dots is spin-orbit interaction. So once again, you start with spin down, and then after some time it goes like that. That is possible, I guess, if the orbitals are coupled, for example. Yeah, there are some admixtures. So spin-orbit interaction, I guess, can play a role in that, facilitate that. But where does the spin go? Yeah, that's a good question. Well, spin goes into the lattice. So spin goes into phonons. And in fact, phonons is what's relaxing spins from down to up. The way to think about it is like that. Spin of an electron is sitting in a quantum dot. And all these phonons are coming. And phonons shake the lattice and distort a bit the wave function and change the electric fields a bit, just very slightly for each phonon. But if you consider the entire phonon density of states, it can be a finite effect. And so after some time of this shaking of the electron, it falls into the ground state and gives its spin to a certain phonon, also its energy. So that's a quasi-classical view of this process. The quantum view is, of course, is just this diagram. You emit a phonon with some spin-orbit matrix element, and you go from one state to the other. They thought they had a proof for the relevance of phonons in the characteristic shape of this relaxation curve. So what they did here is they plotted this energy by just applying different magnetic fields. So what they could also plot on this axis is field from large field to small field. Sorry, from small field to large field. Because at zero field there is a finite singlet triplet energy. There are two orbital states, and then there's coming down at higher field. So this is a low field regime, and this is a high field regime. And they thought that this peak corresponds to when the phonon wavelength matches the size of the dot. So there is some kind of a resonance. When the phonon exactly fits inside the dot, spin relaxation is amplified. There is some kind of a size effect. So their calculation shows that at about this energy, a couple hundred microelectron volts, that's when phonons are the size of the dot. So this is hinting at some spin resonance, and so I wanted to get into spin resonance as the next slide, and then show you how spin-orbit interaction can be used to induce spin resonance. The spin resonance is a very basic concept, but also will be very useful when we talk about qubits. So this would be a concept that comes back a couple times. Just to get us all on the same page, I'm sure most of you know what it is already. Spin resonance is a way to control spin with a relatively small field. So a situation, for example, like this. We have a very large field along z direction, which sets the spin quantization axis. And of course, we could control the spin by turning that large z field in different angles. So if I want to have my spin pointing not this way but this way, I take this z field and turn it like that. Well, it's not very practical. Normally I have to take a magnet which is this size and turn it on the side, something like drastic like that. It takes some time and so on and so forth. You remember spin relaxation times are in the order of seconds, milliseconds, and I cannot turn a big magnet in a millisecond. So, but I have something better, which is this resonant effect. Turns out if I apply just a tiny field perpendicular to the large field, but then I make it oscillate as a function of time, and I do that on resonance, which means that I match this frequency of oscillating field to the spin precession frequency in a large field, to the Larmor frequency. If I do that, I can induce spin rotations. So the way it works is, for example, one simple way to understand it is to go into this rotating frame. It's called the rotating frame approximation. So if we kind of rotate with the spin as it precesses, as it undergoes Larmor precession in this field. So we just rotate with that spin. We can forget actually about this field. It's like that field goes to zero, because we already canceled that effect by rotating with the spin. Okay, we know it undergoes Larmor precession, so let's forget about it. So then, but what we are seeing in front of us all the time, because we are rotating with this field, with this small field, we're seeing this tiny field in front of us all the time. So when we're in a rotating frame, we are a spin. We're pointing along the z direction, and we are not seeing that field anymore because we're rotating, but we're seeing this tiny field, and we're going to start rotating around that field. So in a rotating frame, this field is cancelled, but this field is left, and it becomes a constant because it's rotating with the spin. So then based on how large this is, if this is a field which is normally much smaller than that, then a spin will rotate from up to down by the time governed by this field, how large it is. If it's very large, it will rotate very fast. If it's very small, it will rotate very small. Now, if we unwind ourselves from the rotating frame, we are doing this precession, and slowly we're coming down like that. So like the blue trace here. In the stationary frame, in the laboratory frame, we are doing a lot more precession, but we are coming down from up to down, and then from down back to up. This is what happens on spin resonance. So if we combine the effects of Z and X field, this is what happens. Now if we're not on resonance, well, if we're not on resonance, we can go into the rotating frame, but there won't be a constant field in front of us. That field will be also moving with a detuning frequency. The frequency difference between the Larmor frequency and this omega. And so then the motion that we can expect is some idling around the pole, for example. Another way to look at that, let's go into the rotating frame of this frequency, but then we did not cancel this field completely. There is still a large field here. So then that field will keep us confined to the Z pole. Another way to think about spin resonance is, which I find useful, is kind of the same way as when you are bouncing on a swing, like as a child, you're bouncing on a swing, and your mother is standing next to you, and when the swing comes back to her, she pushes. So she pushes you always at the same phase of your bounce, and that gives you maximum energy. Yeah? So this is kind of the same effect. When we are on this blue curve, every time we rotate by pi, this field, the small field, it pushes you forward. And then you go another swing, and it pushes you forward, another swing. That's the same description. And when you're not on resonance, the field, it pushes you at the wrong moments. And then you turn back before you went for pi, and then you kind of stick around here. You don't go rotations. Okay. By the way, these curves are obtained not for a sinusoidal driving, but for a square wave. That's why they have these sharp kinks here. Now, this is exactly like a mother pushing, a square wave. Okay, so now back to spin-orbit interaction. What I just described to you as a spin resonance, well, that's called electron spin resonance, and it's induced by this magnetic field B0. We can create this kind of dependence by an electric field. If we have electric field of this form, but also spin-orbit interaction. So if we take the electron and move it like that, it will experience an AC magnetic field going like that due to Rashba. So then we can observe electric dipole spin resonance. So this is the same effect, same arrangement of fields, but we use electric fields to control it. So like that, what would be the manifestation of this effect? Well, for example, if you are in the spin blockade situation, remember, if you are in triplet state, you're stuck. So you load into a triplet, and you cannot go forward because triplet 0 is up here. And you have to flip your spin to go. Well, apply spin resonance, and the spins will start to precess. And when they precess to singlet, they can go. So in a spin blockade on resonance, you expect a little extra current, which is what can be observed in quantum dots. So this is, again, a nanowire, gates, define quantum dots, define 2 quantum dots. And then you apply electric field to one of the gates. And it shakes the electrons. I wish we could shake one of the electrons, but we apply a field to this red gate. But actually, electrons are so close, they both are shaking. But that's OK, because they're both shaking, they're both rotating, and they're going from triplet at some point to singlet. And then when we match the Larmor condition, when spin precession frequency from external field matches with the microwave frequency on the gate, we have this extra current here. So here is a plot frequency of driving on the gate versus magnetic field. The slope of this line gives you the G factor. This is energy. Multiplied by h bar, you get energy, by h, sorry. And this is G mu b. This is also energy. So energy versus energy. If you look very closely here, you zoom in here, you actually see that there are 2 lines, somewhat closely spaced. Well, those are from the 2 different resonant conditions for the 2 spins and the 2 quantum dots. The red spin and the green spin are in 2 different dots, because we are dealing with a spin blockade, so we are in a 1-1 state. We are locked in the 1-1 state. And the 2 dots have different shape. 2 electrons occupy different orbitals. They have a slightly different shape, therefore, remember, G factor completely depends on shape. So it's a slightly different shape. They have slightly different G factors by about 0.3 in this material, in indium arsenide. So this is the entire G factor of gallium arsenide, which is 0.44. So in some sense, it's a large difference. But relatively speaking, it's something like 8.9 and 9.2. Those are the 2 G factors we found. And these G factors are also gate tunable. So the difference between these 2 plots, the axes are the same, but the resonances are in different positions, marked by green lines and yellow lines. So the G factors were shifted because we reconfigured the dots, and we changed their shapes by gates. We changed the gate, changed the G factor, changed the orbital size. Through spin-orbit interaction, we have changed the G factor. And we've measured this effect using spin-orbit interaction by applying an AC electric field to a gate, inducing a spin resonance via spin-orbit interaction. So measure the effect of spin-orbit interaction using spin-orbit interaction. This is kind of the ultimate spin-orbit experiment. Now we have to stop. We continue next time with qubits.